Welcome to Stressless Square, where learning is relaxed.
Let's go find them all!
A uniform ladder of length 15 meters rests against a vertical wall, making an angle of 60 degrees with the horizontal. Coefficient of friction between wall and the ladder is 0.30, and between the ground and the ladder is 0.25. A man weighing 500 newtons ascends the ladder. A. How long will he be able to go before the ladder slips? B. Find the weight that is necessary to be put at the bottom of the ladder so as to be just sufficient to permit the man to go to the top. Assume weight of the ladder to be 850 newtons. Imagine you have a ladder leaning against a wall at a 60-degree angle. A person tries to climb it, but how far can he go before it slips? This is the first part of the question. Let's find out. First, let's draw the free body diagram to visualize all the forces at play. The ladder's weight of 850 newtons acts at its midpoint. At the base, we have RV, the reaction from the floor, and at the wall there's RH, the horizontal reaction. But that's not all. Friction comes into play too. Mu RV at the ground and mu RH at the wall, working behind the scenes to keep our ladder from slipping. The man's weight acts at a distance x, representing the maximum height he can climb before the ladder slips. Ensure you note the distances of each force from points A and B, as they are essential for calculating moments. But keep in mind, the coefficient of friction, mu, is different for the floor and the wall. Now let's set up the force equilibrium equations. Since the ladder is not moving, the forces in horizontal and vertical directions must balance out. Also, we apply a moment equation around the bottom to find out when the ladder will start to slip. Considering that the sum of all horizontal forces is 0, we can express this as RH minus mu F times RV equals 0. From this, we get RV equal to 4RH. Similarly, the sum of all vertical forces must also be 0. Now we have the equation RV minus 850 minus 500 plus the coefficient of wall friction multiplied by RH equals 0, with mu F as 0.3 and RV equal to 4 times RH. We calculate RH to be 313.95 newtons and RV to be 1255.81 newtons. With RH and RV now determined, we can find the maximum distance x the man can safely climb from point A at the base of the ladder. To do this, let's take moments about point A. The equation for moments about point A is RH multiplied by 15 sine 60 plus mu W multiplied by RH and 15 cosine 60 minus 850 multiplied by 7.5 cosine 60 minus 500 multiplied by x cosine 60, all equal to 0. Substituting the values of RH as 313.95 newtons and the coefficient of wall friction as 0.3, we calculate x to be 6.39 meters. Now, let's move on to the second part of the problem. In this part, we need to determine the weight W required at the base of the ladder to allow the man to safely climb all the way to the top. Now let's take a look at the modified free body diagram. A weight W is placed at point A and the man's 500 Newton weight is at the top of the ladder while everything else remains unchanged. Before calculating the required weight W, we first need to determine RH and RV. With three unknowns, RH, RV, and W, we cannot determine their values using only the force equilibrium equations, as they provide only two equations for three unknowns. However, by taking moments about point A using the moment equilibrium equation, we can easily calculate RH. The equation for moments about point A is RH multiplied by 15 sine 60 plus mu W multiplied by RH and 15 cosine 60 minus 500 multiplied by 15 cosine 60 minus 850 multiplied by 7.5 cosine 60, all equal to 0. Using the coefficient of wall friction mu W as 0.3, we calculate RH to be 455.21 newtons. Now we can use the force equilibrium equations to determine RV and W. Since the total horizontal force is 0, RH minus mu F times RV equals 0. By substituting RH as 455.21 from the previous equation, we find RV to be 1820.82 newtons. Similarly, applying vertical force equilibrium, RV minus W minus 850 minus 500 plus mu W times RH equals 0. By substituting the values of RV and RH into the equation, we find W to be 607.38 newtons. And there you have it. A weight of 607.38 newtons at the base is just what's needed for the man to safely climb all the way to the top of the ladder. And that wraps up this problem. I hope you found it insightful and easy to follow. If you did, don't forget to hit that subscribe button and stay tuned for more stress-free learning. Keep practicing, because the best way to master engineering concepts is to solve, explore, and challenge yourself. Thanks for watching, and see you in the next one.